So probability distribution. So this again is another major area in statistics. And we have again, two types of probability distributions depending on the variable of interest. So if we have a discrete random variable, then we have a discrete probability distribution or a discrete distribution. If we are considering a continuous random variable, then we have a continuous probability distribution. And so for this case, we are going to consider a discrete distribution. And we are saying some of the distributions that we are going to look include the Bernoulli, we have binomial, we have Poisson, we have geometric and hypergeometric. Now, in this unit, we are not actually supposed to go so much into the details of this because this is the business statistics is the general form of it. So we'll just look at Bernoulli, we look at binomial, and then we also look at the Poisson. So I don't know if at some point you did the series, the sequence and series. I'm not sure, but you should have done that possibly in some fundamentals of mathematics or mathematics for science or somewhere there. But we've already introduced some of these concepts. We did the permutations and combinations. And so some of these terms won't be new. Now, the Bernoulli distribution. So I hope you have writing materials so that you can, as you follow, you note something down. So Bernoulli trial is a random experiment in which there are only two possible outcomes, a success and failure. Now, this means that you are carrying out an experiment and you have an interest of what is going to be the outcome. So you carry the experiment once, then you realize that there are only two possible outcomes. So one that you consider to be success, then the other outcome will be a failure. So for instance, if you toss a coin, you can consider you observing heads to be a success when you observe a tail to be a failure. So you know, we say that the coin has two sides. One is the head and the other one we consider it as a tail. So once you toss a coin, you know how you toss or flip a coin, then whatever lands on the face becomes a success if it is the head, but if it is the tail, then that is a failure. Then again, checking items from a production line. So these were in manufacturing, possibly. They will consider if something is not defective, so that it has met all the features. Then we say that it is not defective. So that is a success. But if you realize that there are some features which are missing, or they are not into, the quality is a bit low, then we have a failure. So phoning a call center. So if I know you've ever made calls, possibly to Safaricom, to Airtel, and at the moment when your call is received, then that means that there was an operator who was free. And so that is a success. But other times you just phone and it keeps ringing and no one is speaking. So at that point, the operator is not free. And so you have a failure. So those are some of the things that you can be able to, we talk of modeling. You can be able to put that, correct such data, and then you record. Then you realize what is the success, what is the failure. Then on that, you attach some probability of success and probability of failure. So a Bernoulli random variable X takes values 0 and 1. That is probability when X is 1. So that means you have a success, then that is P. So P is the probability of success. Then probability X is 0, so that means you have a failure, then that becomes 1 minus P. And remember, we said that the total probability adds up to 1. So you can say that P plus 1 minus P, that will give you 1. So which is the total probability. So you can only have those two outcomes: a success, which you are denoting by 1, or a failure, which we are denoting by 0. Then by definition, so this is the formal definition of this. A random variable X is said to be a real Bernoulli distribution if its probability mass function is given by. So this is the distribution. Now, remember in the previous case, that is on the random variables, we were writing down some functions, but those functions were not defined. They were not defined. So we are simply writing function. We are fx is equals to 2x, fx is equals to 3 plus 4x, and so forth. They were not defined. But now these are an experiment that has already been done, and you realize that it follows a certain, it is a bit systematic, so that every time you can do this, you either get a success or a failure. So these are a Bernoulli random variable, a Bernoulli distribution with a random variable X. So we say P to power X into 1 minus P to power 1 minus X, for X being 0 or 1. So here you can see we have probability X is equals to 1, and here we have probability X is equals to 0. So X can only take those two variables, two values. And so P, we've said P is the probability of success. So you could be told that the probability of success of tossing a coin and you observing ahead, if it is a fair coin, then it means the probability of success will be 0.5. And so the probability of failure will be what? Yes? If the probability of success is 0.5, what will be the probability of failure? I want to know if we are moving together. Okay, 0.5. So we abbreviate this as X follows. So this small sign here, it means X follows Bernoulli distribution with parameter P. P becomes now the parameter, that probability of success. It can easily be checked that the mean and variance of Bernoulli random variable are mu. So we denoted. So for those who have issues with writing the mu, so this is how you write the mu. that is the expected value of the mean, which is P, and the variance, sigma squared. So this is how you write the sigma. Sigma squared is equals to P into 1 minus P. So forget the one here, because it will still be P. So 1 minus P. So in some other texts, you'll find that this will just be, it will be written as Q. The 1 minus P will be written as Q. And so if you find that you have PQ, just know that that Q denotes 1 minus P, which is the probability of failure. Now, we need not to come and start proving this, because again, this bit is just but for the introduction. So you can easily prove that this is actually true. So you have probability for x, 1 minus P, 1 minus x. So you can be able to prove that once you replace, once you know how we do the expected value from what we did, how we go about expectation and variance. So you just need to follow the same and be able to get this. So you know that the expected value of x is the summation. Then you have x multiplied by the P, x into x. So you're multiplying by this function here. Then you know you're summing from 0 to 1. So 0, you just substitute when x is 0. You again substitute when x is 1. And you do the same for the variance. You first get the x, the expected value of x squared. Then you subtract x, the expected value of x being squared. So now, other than the Bernoulli, so we have said, remember, of interest here is to know that you're just carrying one Bernoulli trial or one experiment. And that experiment, there are only 2 possible outcomes. But now, when it comes to binomial distribution, so here we are considering a sequence of n independent Bernoulli trials. So it is one Bernoulli now being carried out n times. So you do it for the first time, you again do it second time, but every time you do that, you again get 2 possible outcomes, a success or failure. So if you write P to be the probability of success of any single trial, then you let X denote number of successes on n trials. Then we say a random variable X is said to have binomial distribution and has probability mass function like this. Now, this part here, we did the combinations. If you can recall combinations. So we are taking n combination X. N combination X now multiplied by the probability of success raised to power X multiplied by 1 minus P raised to n minus 1. I mean n minus X. And you can see the only difference between this binomial distribution and the Bernoulli distribution, you can see that we do not have a combination here. Do not have n combination X. Then P is to power X. But when it comes to this, we have 1 minus X. But here, down here, we have n minus X, to mean that this has been done n times. So n will always be given. You can be told that you are doing this possibly 5 times, you're doing this 10 times, 20 times, and so on. So n is the number of times that you repeat that experiment. Then p is the probability of success. So you'll be told that possibly something like say for a person to score, possibly the probability of scoring a penalty is possibly 0.3. And so this person might try this 5 times. So if the probability of success is 0.3, then it means the probability of failure will be 0.7, because now 1 minus 0.3, that would be 0.7. So that would be given. You just be given the p, that is the probability of success. Then you'll be given the number of times that is happening. Then you'll be asked, now what is the probability that possibly x, the number of successes? You can see here, let x denote the number of successes. So out of the 5 trials, then you can be asked what is the probability that x is equals to 3. And so where you only have x, that is where now you replace. So you're going to have n being 5, x being 3, again here x being 3, then n minus x, that will be 5 minus 3. So that is just but an example. So we abbreviate this as x being np. So we say that x follows binomial distribution with parameters n and p. So the n combination x counts the number of outcomes that include exactly x successes and n minus x failures. So we did how to go about this. That's why we introduced the permutations and combinations way before getting to this point, so that you can easily tell what that is. And so the mean and variance of a binomial random variable are, so the expected value is np, and the variance, that is sigma squared, is np into 1 minus p. Again, I've told you that you might go to some text online or over the internet or from your library, and you realize that this is written as npq. So npq is basically the same as np into 1 minus p. Now, so here they wanted to just prove that this is actually there's a way we say that all the probabilities or the total probability adds up to 1. So that is something that you really need to keep in mind, that the total probability will always be equals to 1. I saw in some text, I think that is something that I talked about now that I've just remembered. We said that for the regression, and that is now on the correlation part, we say that R is between -1 and +1. Now, some of you are just, and I noted that was just guessing, and you see someone writing 20 in that. So if it was anything between -1 and 1, I could tell that you have actually tried to do something. But now writing down 20, I don't know how that was, how you are getting that. And again, in probability, you find that someone is writing -0.5 -3. So the probability, you cannot have a negative probability. It is always positive, and it is between 0 and 1. The probability is always between 0 and 1. So if you get anything outside that, just know that there is somewhere you've made a mistake. So you need to go back and rectify. Always note that it is between 0 and 1. And so this is just but a small proof. It's not something that you really need to work on this, but just know that the total probability will add up to 1. So for an example, so I still again, I hope you're writing down this. So here we have a biased coin. So if it is biased, it means that the probability of you observing head and the probability of you observing the tail, they are not equal. It's not half-half. So the only time you get half-half is when you have a fair coin. But if you have a biased coin, then you toss it 6 times. Then you realize that the probability of heads on any toss is 0.3. Then that is the probability of observing heads. So that is the probability of success, 0.3. So ignore that this is colon. It should be point. It should be 0.3. So let X denote the number of heads that come up. So X denotes the number of successes that come up. So you're told to calculate probability X is equals to 2, probability X is equals to 3, probability. So we did this. So the reason I was confident that we can do this online is because we did this. We know how to, we know what this means. Probability X is equals to 2. We know what that means. We know what, if you say probability X is equals to 3, and where we have a range, we know that what we mean. If you have less than alone, it means that 1 is not inclusive. If you have less than or equals to, then at that point we know that it is inclusive. Okay, so probability X is equals to 2, then you have the number of tosses are 6, so we have 6 combination 2. Our probability of success is 0.3 to power X, so X is 2. Then 1 minus P, so that is 1 minus 0.3, which is 0.7 to power N minus X, which is now 6 minus 2, and you get 4. And so using your calculator, you can be able to get what is this combination multiplied by this to power 2, multiplied by this to power 4, and you just get the answer. So if you write this down, you can then again confirm whether that is correct. Now again, probability X is equals to 3. So where you have X, you know that it will be 3. So you have 6 combination 3. Then you get the answer there. Now, for the case of a range, so you have probability X less than probability 1 less than X less than or equals to 5. So now this one changed. You can see here it is only less than. So which meant that we are not supposed to include 5. Now coming to do the solution here, I've included the less than or equals to. So just note the difference and note why now we have 5 included. So we said that this is the time when X can take the values 2, 3, 4, or 5. So we're using OR, so it means we add those probabilities. So it means that you're going to do this for each one of them. So probability when X is equals to 2, you already have it here. Probability when X is equals to 3, again, you have it here. So you do probability X is equals to 4, do probability X is equals to 5, then you add that. Then you're supposed to note that, again, that probability is between 0 and 1. Any question up to that point? No one with the question? Yes? I want to be sure that you are following, because after this, you're going to get some assignments online and it will be timed. So you don't have time to refer to the notes or something. Any question? So just have an example too. So quality control engineer is in charge of testing whether or not 90% of the DVD players produced by his company conform to specifications. To do this, the engineer randomly selects a batch of 12 from each day's production. The day's production is acceptable provided no more than one player fails to meet specifications. Otherwise, the entire day's production has to be tested. So what is the probability that the engineer incorrectly passes a day's production as acceptable if only 80% okay. So you but I think the calculations are already there, so and you know that this is just but multiplication. Okay, so when I get to a question that is not done yet, I'll just write it down. So for this one, you can easily follow. You can you know, we did combinations. You know that from this bit we have multiplication, then you have multiplication. Okay. So okay, let's check on this second example. So we are saying we are asking what is the probability that the engineer incorrectly passes a day's production is acceptable if only 80% of the day's prayers actually conform to specification. What is the probability that the engineer unnecessarily requires the entire day's production to be tested if in fact 90% of the DVD players conform okay. So we go back again. So someone is asking, how do you do the probability X is equals to 4? So I just explain just the same way you're doing probability X is equals to 2. So you're just where you have X, that is now from the main formula here. Probability X is equals to the small x. So you have the number of times the experiment was done. Then you have the successes that you are being asked. What is the probability of those successes? Then you have the probability of each success. Then once you have the probability of each success, you can get the probability of failure, which is now 1 minus that probability of success. then again that to power n minus x. So the same way you're doing for the probability x is equals to 2. So where you have x in the formula, you substitute with 2. You can see that. The same way you are going to do for the x is equals to 3. So it is the same way that you do for when now x is equals to 4, the same way you do when x is equals to 5. Here. Okay. So that's why I'm saying that you need to write this down. Once you write this down, then now you can try to do this, to do when x is equals to 4, when x is equals to 5. Then now I'll be giving out the assignments. We can change this to some other probabilities. We change the number of trials, and we see how that what that will be. Okay. So we are looking into this, and so here we so this is a manufacturing. So they are testing an item being defective or not defective. So meeting the specifications or failing to meet the specifications. And so in the first instance, we are being asked what is the probability that engineer incorrectly passes a day's production as acceptable if only 80% actually conform to. So incorrectly, then that means that the item will be passed as being acceptable, but in the real sense, it has some defects. And so 80% of that will just be a failure. And so if 80% is a failure, then the success, what will be the success? You see, it can be given as a percentage because, you know, percentage out of 100. So anything that is out of 100, it could be 0 point something, which is again a percentage. Okay, yeah, that would be 20%. The success. So from the statement, you can see that the engineer incorrectly passes. So incorrect, that means that this would just be a failure, but now this person is considering this to be a success. But now with the term incorrectly, it means that now this is the opposite. And so from the solution, let X denote the number of DVD players in the sample that fail to meet specifications. So in part 1, you've been asked the probability that X is less than or equals to 1. So so remember our days, we are considering the days production. So it is just that one day. So that we are going to experience an 80% failure. And so probability that X is less than or equals to 1 will be given by. So the very first thing for you to do is to be able to interpret what does the question require? Or when you say X is less than or equals to 1, what does it mean? And so this means that X is taking the values which are less or equals to 1. And so the values that are less or equals to 1, it's only 0 and 1. 0 and 1. And so to again expand this, you have a probability X is equals to 0 plus probability X is equals to 1. And so we are testing 12 players, 12 DVD players. And so our N becomes 12. And our probability of success, we've said it's 20%, which is 20%. So 20 out of 100 is 0.2. And so you start with the first one, probability X is equals to 0. So that will be 12 combination 0. So you can try to check this with your calculator. The probability that X is equals to, to 0 is 12 combination 0, which is the value of X being 0. Then 0.2 to power 0. So you know anything raised to power 0 is 1. Then 0.8 now to power 12. Then you add that 2. But now X is equals to 1. So where you have X, you substitute with 1. Then you can get that probability. Now, in the second part, you asked, what is the probability that the engineer unnecessarily requires the entire day's production to be tested? In fact, 90% of the players conform to specifications. Okay, so again, you can see there are terms which are, if you're not keen with these terms. So the very first time we had the term incorrectly, now we have unnecessarily. Okay, so that means it's now asking the opposite of we require that they be 90, they conform 90%, but now unnecessarily takes it now to the opposite. And so in this case, 90% becomes the probability of failure. And so the probability of success now becomes 10%, which is 0.1. Now, I think I talked about this. So probability X is greater than 1. So the probability X is greater than 1. You have, so we talked about this. So let me see. So I was saying we talked about this. We said probability X greater than 1. So we know we are considering all the way up to where you have the 12 experiments, or the number of repeated times you have 12. So X being greater than 1, it means that you're taking probability X is equals to 2, X is equals to 3, X is equals to 4, all the way up to X is equals to 12. But this can also be written as, so I hope you can write this down somewhere. So I'm saying that this can be written as probability, where you have x being greater than 1, can also be written as 1 minus the probability now x now being greater than, being less than or equals to 1. So this is basically what I've done here. So instead now of taking all the way from x is equals to 2, x is equals to 3, 4, 5, and so forth. So I've taken now 1 minus probability x is equals is less than or equals to 1. So the probability x is less than or equals to 1. So we've already done that here, but now you can still again do it here, because now the probability of success has changed to 0.1. And so 0.1 plus 0.9, you get that. Now, which means now probability x greater than 1 will now be 1 minus 0.6. So we find that this now will be 1 minus 0.659. And you can try that. You can try that and see whether that will give you 0.34. Although now this one has been rounded off. But you can confirm that that is actually the point. So can continue. So now I'll share the notes so that you can check on this example 3. We have example 3 and also some exercise here that you can easily try. You can, I know you people have groups for discussion. So you can do that in groups as you discuss this, and see if you get similar answers. Then if there is any query, you just ask, but make sure that you first exhaust from your friends, from your colleagues. Just exhaust, and now if anything is not clear, then from there you can reach out. You can reach out to me. So that is on that is all about binomial. Just know that you're carrying out experiments, and those experiments, they have only 2 possible outcomes: success and failure. And so you are given the probability of success, so you can easily get the probability of failure. Then you can get the probability of the number of successes. Now we can talk of another distribution here, Poisson. So I don't know how you pronounce this, because this is not Poisson. It's not Poisson, so it is can pronounce it as Poisson or Poisson. So this is named after this person, the Simeon Poisson. The distribution is used to model the number of events, such as number of telephone calls at a business, number of customers in waiting lines, number of defects in a given surface area, airplane arrivals, or the number of accidents at an intersection. So it's only that possibly I might not require you to go out there and collect some data, but it is very important because these you're able to understand this better when you do it practically. You go out there, you collect data, you do the analysis, and you report. But I don't know, possibly you're going to do that as you do a project later in 4th year or thereabout. You're going to do some research, some project, and so you'll be required to collect data, analyze it, and then report. So we could be able to do this, collect data on the number of telephone calls to a certain business, or even for you, the number of calls that you receive in a day. I don't know how many calls do you receive in a day? Yes. I know some of you receive up to 0 calls in a day. But that does not mean that your relatives have forgotten that you exist. It's only that they're a bit busy. Okay. So you can be able to model that. You can know the success, the probability that a call is received or answered, the number of arrivals of airplane. So you can I think the nearest is Wilson Airport. So you can observe how are the planes arriving, and after how many minutes do you have them arriving? You record that. So the number of hits to your website in a day. So for those of you who have websites, and how you access the website, like the eMasomo. So I can be able to model that, the number of times the students access the eMasomo in a day. So I will record that as the number of hits. So after how long does one take after you log in and so forth? So I can be able to get all the logs in a day. I know when you have logged in. I know when you are offline. I can be able to tell all that. And that reminds me of people who are complaining that they didn't have access, only to realize that they actually logged in the very first weeks. Then I don't know if they forgot or something. So the number of calls that arrive each day on your mobile phone. So this is what I was asking. So how many calls do you receive in a day? How many do you make in a day? The rate of job submissions in a busy computer center per minute, the number of messages arriving to a computer server in an hour, and so forth. So Poisson probabilities are useful when there are a large number of independent trials with small probability of success. Now, this is why we use this kind of probability, because we can have a large number of independent trials, but then with a very small probability of success. For example, if you are to observe, how many SUVs, or say Prado, are passing along the Thika superhighway in a minute. So you can be able to model that. How many are passing? Possibly you're at a specific point, and so you're observing how many are passing. How many Prados do you have passing in a minute? And so you'll be able to model that, and given the number of trials, then the number of successes. Possibly you record how many cars, all the cars that pass in a minute. Then out of those cars, how many of them are Prados? Okay, so that will give you now the probability of success. So you find that it might be very small. It might be very small. Not like when you're considering the Nissan Matatus. So those ones will be many. In a minute, you might find even there are like 500 of them passing in a minute. And then if you put that against all the other cars passing, then you find that it will be a very large probability over a huge probability. So this distribution is used to model those so many independent trials, but now with a very small probability of success occurring at a period of time. So it can also be used when a density of items is distributed over a given area or volume. So here we have the formula. So for Poisson probability with the probability mass function, we say probability x is equals to small x is equals to, so this sign here, this symbol here is what we refer to as lambda. Lambda is L-A-M-B-D-A, lambda. Lambda, L-A-M-B-D for dog, then A. So lambda to power x, then this is exponent. So it is there in your, if you check in your calculator, it is there. It is, I think, above the button with LN after the log, or above the turn button, or below the X button. I don't know, whichever version of the calculator you're using. You can see, you can easily see it. So to access it, you need to take the shift, then LN button for you to get that exponent. Then to power negative lambda, then x factorial. So again, like I told you that this topic is only coming after we've done all this. We've done factorial. From the permutations and combinations topic, we know how we go about factorial. And so what you need to know is, okay, so x is abbreviated as this. You say x follows Poisson distribution with parameter lambda. And we say that lambda is the shape parameter, which indicates the average number. So you realize that in Poisson distribution, the expected value and the variance are equal. So this again is a very unique distribution where the expected value, that is the mean, and the variance are equal, and they're equal to lambda. So if it is given there, then it means that you just need to know what is the lambda, what is the average number of events. So if you're given the average number of events, then the next thing you'll be asked is the number of successes in that. And from there, then you get what that probability is. So these are just values that you need to feed in your calculator. Once you have all this, so let's check an example. Again, this is just to remind you that the probability adds up to 1. So here we have an example. So just to note, the major difference between Poisson and binomial distribution is that Poisson does not have a fixed number of trials. So by fixed number of trials means in binomial distribution, we are talking about n trials, n independent trials. So they are fixed. But for the Poisson, it can go up to infinity. It can go up to infinity because, say, for example, if you are observing the number of Prados passing in a day along the Casper Highway, now they could be very many. You can observe up to thousands and thousands of them passing. So that's why we are saying it's not fixed. It's only that we limit ourselves to a certain amount of time. So say you're going to observe these in just 2 hours. Then in those 2 hours, you record how many successes are there. And then you find on average, how many do you have? So consider a computer system with a Poisson job arrival stream at an average of 2 per minute. So you're having 2 job arrivals every minute. Every minute. Then determine the probability that in any 1 minute interval, there will be, so 0 jobs, exactly 2 jobs, at most. Now, these are other terms that in probability that you need to note. When you talk of, and I hope you are noting down, when you talk about at most, and when you talk about at least, so those are terms that are used mostly in statistics and in probability. So when you talk about at most, we are talking about less than or equals to at most. So that means that you're not supposed to go beyond that 3. So for instance, here we have 3. So at most means it is less than or equals to. You're not supposed to go beyond 3. It's 3 and below. Then when you talk about at least, we are simply talking about greater than or equals to. The term at least, greater than or equals to. So at least means it is from that point and above. From that point and above. So at least is from that point and above. So that is why we have greater than or equals to. And so the average, the job arrivals, we have lambda is equals to 2 because that is the average for every minute you have 2 arrivals. And so we are saying that our average, which we denote by lambda, is equals to 2. So no job arrivals means that x is equals to 0. Now, if x is equals to 0, now if you put that into the formula here, so I want you to put where you have x, just put x to be 0 and put lambda to be 2. You've seen lambda is 2. The average number of arrivals is 2 per minute. So lambda is 2, x is equals to 0. So you realize that everything that is raised to power 0 becomes 1. Then 0 factorial, we said 0 factorial is equals to 1. 0 factorial is equals to 1. So you'll be left with only the exponent to power -2. And that is what you have here. That is what you have here. We're only left with exponent, then to power -2. And you can put this in your calculator and see if this will give you this value. Then when you're talking about exactly 3 jobs, that was supposed to be 2 jobs. Now, I don't know where this kind of excitement was coming from. We are talking about exactly 2 jobs, then here I'm talking about exactly 3 jobs. So exactly 3 jobs. So just know that now these 2 is 3 here. So where now we have x, we substitute that by 3. So again, lambda is 2. So if you just input this in your calculator, 3 factorial, so we saw that we have a factorial sign in your calculator. So just can do it directly, or you can just do 3 times 2 times 1. That will give you 3 factorial. Now, at most, now this is what I was talking about. At most 3 arrivals. So that means x less than or equals to 3. So x less than or equals to 3 means that x can take the values 0, 1, 2, or 3. Because of the equal sign here. Less than or equals to. Because of that equals to, then means 3 is inclusive. And so x can take either 0, 1, 2, or 3. And so now this has just been simplified, but you can easily now, just like we have x is equals to 3. You see how we've done x is equals to 3. So the same way you're going to do for x, you already have x is equals to, you have x is equals to 0. So the same way you do x is equals to 3, you do it for x is equals to 1, x is equals to 2, x is equals to 3. And so just I want you to do this. I want you to do this in the long method. Then you realize that for each one of them, the exponent to power negative 2 will be common. And that's why it has been factored out outside these brackets. Okay, because for the case of x is equals to 3, you have 2 to power 3 and 3 factorial, which is here. 2 to power 3, then divide by 3 factorial. So that is for the place of x is equals to 3. Then you factor out exponent to the power negative 2. Then with your calculator, so these are not things that you can easily do elementary with just your hands. You need to have the calculator. Then where the question now, more than 3 arrivals, so that is x greater than 3. Again, just like we did in the previous case, that's why I have not eliminated this. So we said that you can take 1 minus, because now this x is greater than 3. Remember that this number of trials are not fixed. And if they are not fixed, it means that you can go up to infinity. But because you don't want to go up to infinity, then you just take 1 minus, now x is less than or equals to 3. And you know that the total probability, even if it goes up to infinity, you know the total probability will still have to add up to 1. And so 1 minus that probability, you get 0.1429. 1429. So I don't know if up to that point we have a question. You have a question?
Hello, sir.
Yes.
I'm trying to do the exponent to power negative 2. It's bringing an error. Sijui naiweka vibaya ama.
Yes. I wish it was easy to display, but now I don't know if your calculator is able to is it once you click the exponent, are you getting the power? Does it allow you to input the power?
No, I have to add the power sign, the key.
Okay, then you need to put that into brackets.
Yeah, I've done that already. But it's still bringing an error.
Okay, now I don't know which version of calculator is that. It is written up there. Yes.
FX.
FX what?
82 ms.
80. Oh yeah. So that one you need to be a bit careful.
Okay.
Yeah, because sometimes, and because of the screen is a bit small, isn't it? So
Yes.
which means that you need to always have those. So that means you need to, at least you can see where the exponent is, right?
Yes. Yes.
Which button is that?
The hapo kwa LN.
So above it.
Yeah.
So you shift. So you first shift, you get the exponent. Okay.
Yes. Yes.
Then you click. Now, I don't know which negative you're using, but still from those buttons, up there, after the LN, the next button is what?
Above it.
No, the next one.
Log, then that one for power.
No, the next, that is after it, after log, after ln, then below it you have?
Below it, it's tan, and above it is x cubed.
No, I'm talking about as you move. You see, you move from shift alpha on, then you go to the next line. So I'm talking about the next line. Which button is that?
Oh, it's into bracket negative.
Yeah, so use that one.
Okay. Yeah.
Okay.
Yes.
So
It's
you've gotten it?
Yeah.
Yeah, so you need to use that. Don't use the minus.
Okay.
The operations. Use that negative applies mostly for the powers. So if you have that, you can put into brackets, then you click on that, then the 2. So I hope it is clear even with the others, because I know you've talked, you've spoken for many. Yeah.
Yes, thank you.
Okay. So any other? Any other question? Because I want. Is there any other question?